So today I'm giving guest lecture on the special topics guest lecture on how to how to make robots walk from admittedly biased from mostly optimal control perspective. Yeah, let's get into it. So logistics wise, there's no lecture on Thursday. Don't come in. There's CMU Carnival for those who don't know. We're gonna make an announcement about this, but there won't be office hours this evening. Instead, I will host office hours after class for people that want to chat about project stuff, homework stuff, and life stuff, whatever you want to talk about. So yeah, any questions so far? All right. I'm gonna turn off the audio. So the walking stuff really sort of started in about the 1960s. I'm gonna give a quick intro, a brief history overview for walking robots. It was like roughly in the 1960s to 2000s, there were primarily two groups sort of working on these things. One of which was at Honda in Japan working on the CMU robots. The sort of the modeling choice that they were doing is sort of essentially treating the leg robots as essentially a manipulator sort of pinned to the ground. So every time you make contact with the ground, you assume that you have full actuation. You do the same sort of control strategy you would with a manipulator or a fully actuated manipulator. And this is sort of, I can see from this video, gets some really impressive behaviors back in the day. Let's say I think they were working on this until up to maybe early 2000s, and they were essentially, this was, I would say, the state of the art at the time on sort of bipedal locomotion or legged locomotion in general. Can keep watching this video. But what they're doing is essentially sort of like treating the robot dynamics as a manipulator. And so you can see this sort of the walking behavior is extremely slow and walking very carefully. And with this sort of assumptions, you sort of assuming quasi-static motions and you can't really do anything dynamic. In particular, your robot typically unless you're doing some special heuristics, your robot cannot jump in 2 feet because that would sort of break the assumption that you're fully actuated, your foot is pinned to the ground at any given point, that sort of thing. So that's the. But actually, yeah, when they were actually the later results on this actually is pretty impressive. They actually can do some, even with the set of assumption they're using, they actually can do some fairly dynamic locomotion behaviors. And sort of the other set of work that were. So the other set of research group that were interested in locomotion back in the day were actually from CMU. The famous the CMU at the time CMU-like lab, and that eventually turned into the MIT-like lab, and eventually turned into Boston Dynamics. This is, I think, a lot of this work was done in Wien Hall. I think the woman in the back might be Jessica Hodgins, Professor Jessica Hodgins in the RI, who's a PhD student at the time working on these things. And in this sort of paradigm, they were focusing on, in particular, dynamic locomotion. So modeling your robot with a floating body dynamics. And this is the so-called the Raybert hopper named after Professor Mark Raybert. So in this case, they were sort of like doing very sophisticated dynamics modeling, leveraging insights from stability and so how do you stabilize the unstable plants in real time by hopping. And this is, have people seen these videos, by the way? Okay, yeah, these are fairly famous videos. Hopefully, if you haven't seen them before, I'm showing you them now. But people can do, this is a lot of these things were done at CMU, and I think this is a wing. This is the first floor Wien Hall. And they're doing the quadruped robots that eventually turned into a lot of these ideas that turn into the Spot robot at Boston Dynamics, and eventually the Alice robot. Here the actuation method I believe is hydraulic. That could be wrong. And the point is they were doing fairly sort of weird hopping behaviors, and this is almost completely contradictory to the Honda robots that we were seeing earlier. where everything is quasi-static, and almost you have to in this case you almost have to be hopping at any given point. So sort of fast forward this a little bit in the 2010s, the actuation methods have been a little bit more mature. People designed the Boston Dynamics designed the hydraulically actuated the Alice robot. And here this is taking the floating-based dynamics a little bit further and using sort of modern numerical optimization methods. Here they're doing nonlinear model predictive control to get some of these very dynamic parkour behaviors on Alice robots. Sort of personally, this is when they were doing this, roughly 2018 is when I started college and sort of definitely motivated, trying to understand some of these things and eventually go to grad school. Sort of around the same time, there's also been a shift in actuator technology, particularly sort of, I would say, in particular, the MIT mini Cheetah robot. A lot of these control methods are actually, they're new, but the fundamental innovation here is actually they made actuators electric. They essentially sort of standardized the direct to drive or quasi-direct drive electric motors. They are sort of much easier to model than the hydraulic actuators that you saw on the Alice robots, and much cheaper to manufacture. And once they sort of, I think I consider sort of MIT Cheetah robots to be the turning point for modern Lego robots. Once they sort of started open sourcing their design and control methods, you start seeing a bunch of companies can reproduce their results and manufacture them very cheaply, and eventually turned into all the robots you can buy very cheaply today for a couple $1,000s. And the control method they're doing here is something called Convex MPC, which we'll discuss a little bit in this lecture. In particular, usually doing you can do like fairly agile behaviors, doing backflips and walking on a bunch of uneven terrains and that sort of thing. So that's sort of the actuator story. And fast forward to 2025. Have people seen this video, by the way? Hopefully, this is like all over YouTube, LinkedIn, all the social media platforms. So fast forward to 2025, all the sort of the direct-to-drive electric motors have become sort of the standard. And sort of the control strategy wise, in terms of control strategies, these days is RL sort of all the way. MPC was essentially the state of the art in probably the late 2010s, and RL has in the 2020s, RL has been shown much more promise. In particular, here they're doing not just RL. They're to make these robots walk like people. And you see the smooth motions that looks like people is because they actually have motion capture human movements, and essentially design the RL rewards to mimic the human movements. I think I forgot if I read this somewhere or someone told me. Boston Dynamics is actually here doing some combination of reinforcement learning and MPC online, but maybe don't quote me on that. Some fairly impressive parkour / breakdancing stuff. So yeah, to sort of like summarize the history of walking robots, people started building these systems in about the 1960s and sort of picked up a bunch of steam roughly in the 80s. The earliest results were from the hopping robot at CMU, and the Honda results are both from the 80s, I think. And so in terms of modeling approaches, the Honda guys were doing essentially inverting an arm and sort of modeling your robot that way, and the floating and the MIT CMU people were modeling the robot with floating body dynamics. By the way, if you're doing RL, you're still using, you're still modeling the robot with floating body dynamics because your, simulators are typically simulating the floating body. In terms of actuation method, hydraulic, if you wanted, let's say 10 years ago, if you wanted high performance actuators, typically you have to do hydraulic actuation that are, super nonlinear and hard to model. And these days, the direct to drive electric motors are very cheap to manufacture, easy to model, and that sort of thing. So that's sort of the standard. In terms of control strategy, model-predictive control was, I think, in the late 2010s, the state of the art that enabled a bunch of the cool behaviors. And roughly, I think I would say around ever since maybe the early 2020s and eventually 2021, 2022, a bunch of the RL methods have sort of caught up. And I think this is, I would argue RL is the state of the art, and this is what all the companies are doing. And yes. So that's that. So the first sort of control algorithm that we're gonna, yes, Gary?
Could you tell me a little bit about the quasi-static there?
So the quasi-static means you're sort of assuming that your robots are moving really, really slowly. Similar to like, the industrial robot arm that are like, moving like this. That's sort of what they were doing. Yeah.
So the velocity is zeroed out.
So the velocities, we're sort of assuming the velocities are really small, and sometimes you can throw all the velocity terms in your mass matrix, for example. Yeah. Yeah, but that's that makes the control problem easier if you can assume the quasi-static sort of thing. So the first sort of control strategy we're going to talk about is called Convex MPC. This is what the standard roughly in the 2017, 2018 when the MIT Cheetah robot first came out. Roughly, this is we actually have done this in this class, I believe. This is essentially a quadratic program. You wrote your own quadratic programming solvers for homework, hopefully. What you have here is actually have a quadratic cost and some linear robot dynamics model and a linear set of constraints. What's nice about this problem is that this is a convex optimization problem. You're guaranteed a solution. If you're
done with it, just do validation.
If you find a solution, it's
if you're done with it, make it
global,
validation new.
optimal solution. You can solve this typically pretty
under
quickly,
annotation, you
on
can
pretty
choose
resource constrained computers.
Choose the validation. So go back to the
so
job.
all of that stuff is really nice. And sort of the way people have turned the control problem into a convex program is by first, instead of thinking about all the articulated bodies of a Lego robot, the standard thing to do to sort of make this thing convex is simplify the model to just a single rigid body. There's a bunch of names to this attached to this model. We typically call the single rigid body model. Some people call it a lumped mass model. So you assume all the mass sort of like is centered around the base. Some people call this a potato model. It's just a floating potato in the air. If you stare at this a little bit, this kind of essentially looks like a quadrotor, and with actuations on essentially the forces coming from the feet. So the whole pipeline for doing this here, again, the single rigid body picture on the top right, sort of the entire system diagram looks like first you have a state estimator. You need some state estimator from given some sensor measurements from your joint encoders, IMUs, that sort of thing, and typically have some contact flags. And you spit out the position attitude of the robot at least for the single rigid body model that you're using. And you have a gait and footstep planner that's you typically plan the footsteps with some sort of heuristic. And what this sort of gives you is it gives you a contact mode that you feed into your MPC solver. And also sort of for the legs that are not in contact with the ground at any given point, it gives a swing leg trajectory. So it tells your robot how to move in the between contact modes. And finally, the MPC solver takes in the state estimate from the estimator and the contact mode. And what it produces, it solves the convex MPC problem, which is the quadratic program that we saw earlier. And it gives you a set of contact forces that you want in the future to sort of balance the robot, track a certain velocity, that sort of thing. And eventually you have some of the joint level controller that maps essentially the contact forces you expect from your feet into the executable joint level motor torques. You essentially have some inverse kinematic mapping from your feet to all the joint torques. And then finally you send the torques to your robot, and your robot gives again on the sensors from your robot, joint encoders, IMUs, foot contact, contact flags / force sensors potentially, and then you do estimation all over again. So this is sort of the standard setup for doing I would say convex MPC / hybrid MPC. There are a bunch of names for it. Basically, you sort of the point is you sort of decouple the contact footstep planning problem to the MPC problem where you're sort of given a set of contact flags or contact modes. That makes this problem much easier to solve. There's some other methods that are trying to solve jointly the footstep planning problem and the MPC problem. Those are typically gets a little bit fuzzy and annoying, and this is sort of a more complicated system, but in practice sort of works pretty well. And the heuristic, by the way, I don't think I have time to go into the heuristics for the contact planning, but this is typically what's called the Rayburn heuristic. If you want to look up what that is. Basically sort of tells you for a given body velocity that I would like to track where I should place my feet heuristically, instead of solving the contact planning problem that are generally combinatorial and that sort of thing. So the assumptions for this sort of convex MPC paradigm, yeah.
How many contact modes typically are?
So you have 4 contact points, let's say on the feet. And at any given point, each of them, at any given sort of like time step you're optimizing into the future, they can either be in contact or not in contact. And you have 4 of them, and that's, I guess whatever that is combinatorially. And that's not including the friction cone. You can also be sliding. You can also technically, there's also a binary mode thing with either sliding or like in sticking contact. Yeah. So that problem sort of blows up very quickly. Yeah, what's up?
In the, I guess it'd be negative, but at some point you basically just set limits on like how much tangent force you're allowing each foot to apply.
Yeah. So that's still part of the linear MPC. So typically we do like a linearized friction cone. So those constraints end up being linear. So you can just fit into the QP nicely. Okay. Yeah. So that's where you throw the friction cone is where you throw in the linear MPC, and that tells you how much tangential force and normal force you can produce at any given footstep. Yeah. Nice. So the assumptions that we're making here is that number one, the leg mass are relatively can be ignored, or are much smaller than where you are the body mass. This is sort of like essentially sort of a function of a control and design co-optimization. And when people sort of came up with a control strategy and designed the robot simultaneously, and eventually people essentially put the batteries and motors, that sort of thing, essentially on the base of the robot. So particular for the MIT Mini Cheetah robot, this is a really good assumption. The legs end up being very light, and all the motors are sort of around the base. But let's say for more complicated humanoid robot, this might not be such a good assumption. And the number two, sort of to make this problem, if you make the dynamics linear, the single rigid body model, if you take that, is still a nonlinear model. To make the problem linear and convex, you have to do the same sort of linearization you do similar to a quadrotor, where you sort of assume the small angle approximation, and essentially take a single linearization for your floating body model. So that's sort of what makes the problem convex, and can solve this with just a QP. And then finally, you're sort of assuming you can, if you're given some sort of like, contact force that you want to track in the future, you're assuming that your robot can track those sort of foot positions relatively well, aka sort of the contact modes that you want from your foot to track your robot can generally do that. If you sort of have sort of contact mode mismatches, that can be really annoying. So the swing-like controllers, you're assuming that you can sort of swing your leg to any arbitrary position at any given point, subject to maybe the physical limits of the robot. So generally, so people like these things. At least this was the state of the art for a little bit. Generally, this is very computationally inexpensive. You can solve the QPs at hundreds of hertz on pretty small onboard computers. Even 2018 was 7 years ago. Computers were much smaller. You can solve this problem pretty quickly. And the annoying thing is that the linearized single rigid body model can be limiting at some point. We're doing essentially 2 layers of model simplification. We're reducing the order of the robot to just a single rigid body, and we're linearizing. Which is sort of the more general methods. Typically, you want to do. Ideally, if compute sort of wasn't an issue, you ideally do some sort of nonlinear MPC, where you're taking a nonlinear single rigid body model, or if you have more compute, you can do a whole body nonlinear, the entire whole body model of the robot. But then the trade-off there is that one, you have to spend a little bit more time on the compute because you need to relinearize the robot and that sort of thing. And you get a non-convex optimal control problem that you're not really guaranteed solution. You have no guarantee on sort of any sort of optimality, that sort of thing. But that, typically that's usually not an issue because you're warm starting from your previous solution. So it's typically is fine. But, rigorously speaking, you can't say you sort of have any sort of optimality guarantee in the general case. So sort of one way to getting at the nonlinear MPC is doing iLQR. This video is from a recent paper that we did running iLQR with Mujoko. Can play this video. So what we're doing here is sort of like taking the Mujoko dynamics and essentially just running iLQR. What I'm showing here is that on the left I have the Mujoko simulation GUI. And the task to walk around and track this green ball, and I can drag around this green ball. I can see the predicted trajectories in purple, and I can see everything my robot is doing in real life directly. And essentially on the left is a digital twin. I can see everything that my planners are doing, all the hyperparameters in my MPC controller. So this is sort of works extremely surprisingly well, I would say. For such a simple method, we can do sort of bipedal walking with a quadruped. Essentially, we like tried this. This kind of just worked first shot, and it's kind of amazing. It's nice when things work, because usually they don't. And we can do what's sort of nice. The nice thing about sort of the MPC methods versus I would say RL is that you can plug in a different robot and sort of run the same controller without any sort of offline training. So we just swapped out the URDF files / XML files from Mujoko and put in go-to robot, and then we can do the same thing, dragging the robot around and tracking the green ball. We have a little bit of humanoid results, doing very vanilla sort of simple trouting, that sort of thing. All again just doing iLQR. So that's that. So the takeaway here is that sort of, iLQR, at least naively, doesn't really handle any sort of constraints. And the way we're doing it, we're not really handling the contact constraints per se. All we're saying is that we're rolling out the dynamics in the forward rollout with the Mujoko contact and friction models, and we're linearizing the robots with all of those contact with all the contact and weirdness. And surprisingly, that works. We actually, in fact, are not really doing anything smart with the linearization. Typically, differentiating through contact can be tricky and annoying, and we're here, in fact, are just finite difference, using finite difference to get the dynamic Jacobians. And two, sort of the iLQR algorithm, I would say, sort of dates back to the 1960s. I think is when the first DDP algorithms were introduced. We're really not doing that many fancy things. We're essentially taking a really, really old algorithm and just putting them on modern computers. And it turns out with computers got faster and really old algorithms just started working. I'll say, there's over the last, 10, 20 years, there's been a little bit of progress on robot simulation. In particular, these simulators are more accessible, and I think at this point, people know how to sort of simulate rigid body dynamics and the point to surface contact pretty well. So that had a little bit to do with why things are working today. But mostly I would say sort of computers are, compared to the 1960s, mostly computers just got so much faster, and we can do just sort of take a really old algorithm and throw out modern computers and get cool results. But I think in general, sort of nonlinear MPC is still an active area of research for Lego robots. There are a bunch of things you can do here. You can do nonlinear single rigid body models. So we discussed this a little bit earlier, or you can do whole body dynamics. It's still in the general case, still pretty computationally expensive. You have to do sort of a bunch of factorization, linear algebra, gymnastics to get these things to run in real time. I think there's a little bit of it's still unclear to I think most people if you should do iLQR versus sequential SQP or sequential quadratic programs for this nonlinear MPC. Do people know what's SQP, by the way? Do we discuss? Okay, so it's in the iLQR case, you get for free the linear time varying linear feedbacks. That's actually part of what made the demos I showed you earlier work is because the iLQR solves can be somewhere between 50 to 100 hertz. But in between the LQR solves, I can apply the TV LQR feedback gains on my robot, and that sort of stabilizes the system in between LQR solves. In the SQP setting, it is much more general in the sense that I can add more arbitrary constraints like contact and friction and maybe arbitrary state constraints. So it's much more general in that sense. But you don't, at least naively, all you get is an open loop control trajectory at the end, and you don't necessarily get the feedback gains for free. So I think there's still a little bit of discussion whether you should do iLQR or SQP for these things. And by the way, iLQR, you can also sort of do, if you want to add constraints with iLQR, you can also sort of do what's called augmented Lagrangian methods and that sort of thing. So it's still possible to do iLQR with constraints. It's just not something we're doing currently. And I think in general, what the other sort of active area of research is sort of differentiating through contact and letting your optimization solver reason about nearby contact modes or the so-called contact implicit methods that you don't necessarily have a fixed contact schedule for your robot to track. And you want your optimization algorithm online in real time, figure out sort of where to the timing and the mode schedules and that sort of thing for your robots. So that's sort of it from the nonlinear MPC side. Are there questions? Thoughts? Okay, cool. So we sort of hinted at this a little bit earlier in the intro slides. Reinforcement learning has sort of really taken off the last let's say decade. What reinforcement learning does is sort of you typically have some agent modeled by a network, and you have the agent take some actions and with some environment, typically in simulation, and what it produces some sort of reward, and you do this over and over again, typically offline, where you can collect lots and lots of data. Typically the optimization is done offline, and at test time all you have to do is deploy a network that's pretty easy to inference and that sort of thing. This is sort of extremely clean in the sense that this the data and compute scale. This should just in principle works much better. And this is essentially sort of what happened. I would argue the main reason behind the RL revolution has been sort of compute and availability of simulation data for these sort of locomotion tasks. In particular, there's been lots of off-the-shelf GPU accelerated simulators. You don't need that big of a GPU to get thousands of robots simulating in parallel. Most of the standard ISIC gym, there's new simulator coming out every other day, but ISIC, Mujoko, all that stuff sort of parallelizes extremely well on standard desktop or even laptop GPUs. And sort of the other thing I would say what made RL work is that people have sort of mastered the art of having good enough physics for these set of locomotion tasks, and also sort of generate large sets of data that can satisfy the RL data hungry appetite. In particular, people, the sort of the point point contact to surface simulation is fairly good, and it doesn't capture all of the physics, but it's sort of good enough for a robot to walk around, and even can be quite robust sometimes. But I would say for a lot of the manipulation settings, I would say the simulators today are not quite good enough, and people are still actively working on those things. And so the other thing that's sort of powerful with reinforcement learning is sort of you're amortizing the compute offline compared to MPC, where we're solving the optimization problem in real time on the robot online. What RL is doing, sort of solving the policy optimization problem with lots of compute offline. And at inference time, it becomes extremely cheap and easy to inference. You can put this on just a very small computer typically on board on the robot, and that'll just work. So and with reinforcement learning, you also get sort of a much richer set of representation compared to MPC, which is I would say that's another reason why that's RL stuff is sort of the state of the art these days. By much richer representation, I mean you can do sort of vision based, so you don't necessarily have to do the state input per se. You can sort of do egocentric vision. There's been a lot of work from Deepak's lab at CMU, a lot of stuff from ETH from Marco Huder's group. Doing this sort of thing. And you can do, because you're optimizing your policy offline, you can do all sorts of domain randomization, make your policy robust. You can train your policy such that it can adapt to sort of a little bit of online data as sort of the rapid motor adaptation story from CMU/Berkeley. And additionally, you can directly sort of train your policy from sensor inputs to torque outputs without the explicit estimation representation. You can just do directly learn your policy from sensors. I would argue sort of the main reason why people don't do MPC these days is because the estimation is very annoying and the whole system takes a while to set up. Sort of empirically speaking, I would say when I started grad school, people would spend to replicate the MIT Mini Cheetah controller, people would spend about 6 months to a year, let's say, for a PhD student at the time. To replicate that results, and then sort of building on that, sort of the life cycle for that sort of research ends up taking much longer than git cloning something on GitHub and adding a couple rewards terms and maybe update the policy a little bit more clever with some clever tricks, and so the research velocity in that direction is much better. Okay, I think I'm going really fast. I'm going to run out of slides very soon, so please ask questions. So sort of the open sort of research question is that given RL has worked so well by leveraging sort of the parallel computation in the offline setting, there's been a lot of recent interest, in particular from CMU, from our lab and from Guanya's lab, on thinking about how can we leverage this sort of set of parallel computation at test time. And sort of one set of algorithm to do this is called, have people heard of MPPI? Okay, I'm going to give a really brief intro on MPPI. Roughly the way this thing works is sort of you have some initial distribution of the action. So for say you have some initial some mean and covariance on the actions. What you do is sample from this set of distribution and you roll them out through your simulator, through a dynamics model or whatever. And you evaluate these samples based on the whatever cost function. It could be the standard cost function used for MPC, RL, whatever. And then you essentially sort of pick the best one or do some sort of weighted average of the top couple of samples, and you sort of update the mean of the distribution to the average, the average of top couple candidates. And you sort of do this over and over again. And typically you typically sample once and pick the best one, send it to your robot, but you could also in principle do this over and over again if you're happy with your answer. Sort of the visualization, my collaborator Juan made this visualization, sort of the sampling process. Here for a quadruped, it's sort of sampling a bunch of trajectories and picking out the best one for the robot to execute. And to do this, you can do this over and over again, execute on the robot, that sort of thing. Yeah.
Is that still using a similar model we were talking about with the Cheetah robot, where it's like a point mass?
Yeah, that's a really good question. So here we're not. So turns out the computers today are fast enough and simulators are fast enough. We're not doing model simplifications at all. We're just rolling out the whole Mujoko nonlinear whole body models, and turns out that just runs in real time. Yeah.
Based on this visualization, it looks like it's sampling in a sort of a restricted area. Is there a constraint that forces the sampling in that area, or if it's just randomly sampling, why is it not sampling some art place?
Yeah, so you have this thing for this sort of things to work well, you typically have to tune the covariance matrices. Typically you want your especially in the limited samples, you want your you sample in a close sort of trust region type thing. You don't want your robot to arbitrarily explore most of the samples, don't go anywhere. Yeah. So the reason for doing MPPI and the reason why MPPI has been popular for some other applications is that one, MPPI is extremely sort of parallelization friendly. You can run these, you can roll them out in on sort of big GPU, beefy GPUs that you have. Basically, this entire process, right, is entirely in parallel. You can evaluate all the samples, evaluate all the costs, and do the update essentially all in parallel. It's completely derivative free. So instead of for contact-rich tasks, basically before I have to like do arbitrary, I have to think really hard about how I differentiate it through contact dynamics, which are generally typically non-differentiable. Depends on the model, is either really stiff or non-differentiable. But for MPPI, I don't care because I'm just simulating through the arbitrary contact model that I want to use. And because it is derivative free, it sort of naturally incorporates black box models where you can sort of model the dynamics as arbitrary neural networks, and you can think about learning the dynamics or the simulator, if you will, with the arbitrary function approximator, and sort of just because all you're doing is solving the forward simulation. The con is the reason why people don't do this for high dimensional system is essentially the curse of dimensionality. Because you're doing this sort of random search type thing in real time, it doesn't really scale with the number of control dimensions typically. And sort of, I'll say in the last 5 to 10 years, the most successful application for MPPI has been sort of off-road autonomous driving, where MPPI is basically the standard. If you talk to, I think, folks at CMU working on autonomous driving in Basti's lab, I think some other groups, like MPPI is the stock controller, basically, because in the off-road autonomous driving case, you have a relatively small number of control dimensions. You basically control the steering, acceleration, that sort of thing. And you're also typically dealing with pretty complicated dynamics that are hard to model. So that you can think about learning the interactions between your wheels and off terrain dirt and mud, that sort of thing. And MPPI can do that sort of very, very naturally. So we sort of like there's we've folks from our group, in particular me and my collaborator Juan and some folks from Guanya's lab have been thinking about doing MPPI on Lego robots. I'm gonna sort of talk about my take on this. Feel free to ask me about the other stuff later. But sort of, I would argue sort of the reason to do this is actually simulators have gotten and computers have gotten pretty good. And so good that you can sort of simulate basically all the physics a simulator can give you in real time over 100 hertz. And this gives you sort of the reasoning capabilities over basically your whole body model of your robot. So instead of basically in the Convex MPC setting we saw earlier, where you're modeling your robot with a single rigid body and you only consider foot contact, you can't really consider all of the collisions between, let's say, the shin of your robot or the body of your robot. Here, because I'm using off-shell simulator, I'm just like doing dumb parallel simulation. I can get all of those physical phenomena in my parallel rollouts, and that lets me reason over pretty interesting behaviors like climbing on top of a box with leveraging using sort of shin and elbow, that sort of weird sort of contact dynamics that are typically hard to plan for and hard to model in the general MPC setup. And also gives me the sort of I can also sort of think about doing manipulation with this, where in the middle example, all I'm telling the robot is to I don't have any sort of planned contact mode. And all I'm saying is like, there's a box over there, go walk towards the box. And I want the reward term says, I want the box, let's say further away where the yellow dot is. And MPPI sort of like in real time, all sort of reasons over basically everything the simulator can sort of give you. Yeah.
How do you come up with a decent guess at like the future trajectory distribution that you're sampling from? Because like, especially climbing up on that box, that feels like you would have to know roughly how to go up and forward, that kind of thing.
Surprisingly not.
Okay.
So basically what we're doing here, so we have a sort of a reference gate. So the reward is on some to track around some reference gate based on the Rayburn heuristic, basically, the standard stuff. And it's sort of the rest are just basically the MPPI just coming up with the gate sequence to climb up on that box. Yeah.
The behavior that MPPI can perform like limited by the horizon which we are rolling out, right? So it
Yeah.
can't give, I'm assuming you can't back it because for that you need a kind of a way longer horizon rollout.
Sorry, which task are you discussing?
Just using MPPI, it is like, we can't apply it everywhere, right?
Right. It's still like a local optimizer. Like it's a little weird in the sense that it sort of like explores multiple local minimas before sort of converging to like one of them. It's like in the limit of like infinite horizon, it is like does sort of a global E search, but it's not like I still consider MPPI sort of a local method. Yeah. But yeah, that's a good question. But yeah, you obviously can't foresee sort of like future contact behavior that are not in your like prediction horizon. And yeah.
The first task, right, as the robot starts off a little further away from the box, it's first flying, and then it gets closer and closer.
Yep.
So at the point where it's trying to, first time it attempts to climb, that sampling horizon, you would never have sampled, like, you have to sample a little bit above, right? So to sort of like to make the move. So you would never have sampled there before. So how does the covariance matrix evolve?
Yes, so that's also a good question. So we're not updating the covariance matrix. For different tasks, I think we tune the covariance matrix to sort of like encourage exploration a little bit sort of manually. But we're not doing anything smart with regard to like sort of updating the covariance matrix, that sort of thing. Yeah.
Can you go back to the slide with like the rollouts being visualized?
Sure. Oh, yeah. Oh, actually, I have a couple Zoom questions. Yeah, sorry. Yeah, what size? You can go first.
Yeah, so like when it's doing that, those are each individual rollouts. So like the
Yeah.
covariance matrix there is tuned to not try to go up.
Yeah.
Right,
Yeah.
okay.
Yeah, but also like it's also a function of the reward. The reward is to go straight. So like it sort of makes sense that most of the rollouts want to go straight ideally. But with the reward, if the goal is like up top, you can ends up sort of discover some behaviors to like make the robot jump and that sort of thing.
While I was doing one rollout, is it still trying to like at every time step in that rollout, trying to pick the best action that gets it closer to the reward? Or is it just rolling out and then evaluating the entire thing?
It's evaluating the entire thing.
Okay.
It's like the so-called single shooting, right? Like you're optimizing over the set of controls, and you don't really, and you only recover the states from the rollouts. So a couple Zoom questions. How do you get the distribution? Yeah, so I guess basically you choose some initial mean and some essentially fixed covariance. This is like the simplest way to do this. Second question: are we creating distribution by generating actions? No, I guess it's the distribution is, at least the covariance of the distribution is fixed, and then we're just updating the mean, if that makes sense. This is like the most like vanilla like implementation of MPPI. Like there's lots and lots of modifications to this algorithm. You can do much smarter things. I guess what we're showing here, you can do some really simple and vanilla things and get really cool results. But yeah, those are good questions. So we talked about that. So it turns out a lot of these behaviors actually translate to the real world. In particular, we can do some standard walking. There's a little bit of robustness. We poke it around. So there's some unmodeled behaviors, some unmodeled disturbances and collisions and that sort of thing. And we can do sort of the jumping. So we can jump on top of a box, roughly the size of the robot. It can do actually some pretty interesting. It's getting the push box example to work was kind of fun. Seeing the robots actually push the box in ways that are completely sort of unplanned and in the reward function. And a lot of these things essentially sort of basically works out of the box. And sort of the one surprising bit, and I would argue maybe you actually turns out you don't need that many samples. And I would argue you want to sort of live in in the small sample regime, and you sort of update your policy quickly, which is maybe sort of the main difference between sort of our stuff versus some of the other folks doing MPPI, trying to do MPPI for Lego robots. I think the other papers are typically trying to sort of parallelize as much as possible on a GPU. And I would try to make the argument in this slide, basically for GPU simulation, you're simulating some arbitrary function or dynamics function on the GPU, because there are lots of cores on the GPU, but the individual cores are much weaker than something on the CPU. So you can imagine, the simulation rollout, you can do this, very slow. You can, on the GPU it's much slower. You get lots and lots of samples in parallel, but individually they're all really slow. Versus on a CPU, it's much more the general purpose. The cores are much more general purpose. You can get the simulation back much quicker. And I would argue in fact, for real-time control, you want to sort of close this real-time feedback loop, as opposed to thinking about getting as much samples as possible and finding a better local minima, let's say. Because I would argue, sort of philosophically speaking, when you're doing real-time optimization, real-time optimal control, the longer you spend optimizing a set of problem from arbitrary given previous state, the longer you spend optimizing that problem, the longer your robot sort of drifts from the problem that you're solving. So if you sort of spend all the compute solving one problem sort of perfectly, I would argue you're fundamentally solving the wrong problem. And what you want is, in fact, sort of close the real-time feedback loop quickly and get an answer that's better than the solution that's currently running on your robot, and send the current best robot, the current best solution to your robot, and do that as fast as possible. Yeah.
Does that latency come from the GPU cores individually being slower, or is it like a communication latency between like the VRAM?
The individual cores being slower. You can sort of try, simulating with, let's say, JAX, and sort of like if you sort of don't max out the number of cores, if you want to like generate, let's say, like 100, 2,000, or a couple hundred samples, you can, if you want to simulate all of these like sort of contact behaviors, and maybe you get the samples back from maybe let's say 10 hertz or 1 hertz, something like that. Versus on the CPU, if I'm only simulating tens of samples, I can do this on basically we're doing this on an Intel from an Intel i9 machine from the last couple of years, not even like the best of the are. We're looking for something with fast single core performance, with, let's say, like 20 cores, let's say, and that sort of gives us let's say 20-30 samples at over 100 hertz, and turns out in my experience that I would argue that's what you want. So sort of like the one trick to make this all work. So we discussed this earlier. The MPPI is naively does not work well at all for high dimensional systems. The quadrupeds we're controlling has a 12 number of actuators, and this is naively this does not, MPPI shouldn't scale at all. You typically want lots and lots of samples. And sort of I would argue that the one sort of key trick to make this work is sort of compressing the number of the essentially the prediction horizon, the number of degrees freedom in the prediction horizon, into just a couple of control splines. So instead of thinking about, let's say if I want to predict half a second into the future with 50 time steps with 50 time steps, so sort of instead of like optimizing over all of those controls at once, I can instead sort of compress my control representation as a cubic spline, and instead I can, if I only sample over on the control points or the spline points, I essentially have reduced my search dimension by 10 times, and that sort of makes my search problem much more tractable. And the other sort of nice thing about doing this is that now my actions that I get from my MPPI planner are guaranteed to be smooth. Typically, if you're doing something like MPC or reinforcement learning, you typically have to sort of add some sort of regularization to encourage smooth actions, so that the outputs from your optimizer can actually get transferred to your robot. For if you're running MPPI and you're doing a spline representation of the controls, you just get that for free, and then turns out things transfer pretty well. Yeah.
So when you said you restricted, the spline thing.
Yeah.
So when you restricted to 5 control points, are you saying that for the horizon, each of those controls have to follow one of the spline trajectories?
Yeah, so basically each like actuator is represented as a spline. It's like, yeah, so I'm like basically I'm still only sending the first control to my robot. But it's just that like my prediction like becomes like a cubic spline of controls. yeah, I'm not sure if that I got your question completely, but so that's all cool and good. So there are so sort of many cases where the simulated physics actually still diverge from the actual physics in real life, especially when we're dealing with, in this push box example, we're dealing with pretty complicated sort of sliding friction that are potentially not at all modeled in the simulation. So I would say we're pretty good at this point between simulating point to surface contact. But some of these sort of more interesting sliding behaviors and more or simulation, collision with weird geometries, I would say we're not quite there yet. In particular, the second task, we're asking the robot to slide the box across the floor, not just pushing it forward. And there, the sim to real gap ends up being much bigger. Oh yeah, we put mocap markers. Yeah, so basically the box show up in the model, and the robot predicts interactions with the box. Yeah.
If we were to use ILC, then does the policy sort of learn the friction dynamics as well?
I haven't thought about ILC in the context of MPPI. Potentially. Well, your policy is your like open loop control sequence. Like that's your sort of policy that sort of gets updated in real time online, that sort of thing. But yeah, typically, when I think about ILC, you have some you're rolling out some set of fixed policy, where MPPI, you're sort of doing something random every time. So I'm not sure how that would fit in. But that's a good point. I think broadly, I would argue sort of when you're dealing with sort of weird sim to real things, you either want to sort of somehow update the model or you update your policy to sort of close this sort of so-called sim to real to sim gap. All right, nice. So sort of the second sort of fundamental limitation I would argue for MPPI is that you can only sort of control what you can simulate. This is broadly true regardless if you're doing reinforcement learning or that uses some arbitrary simulator or optimal control. But in the MPPI setting, not only do you have to simulate to control, you have to simulate things very fast and in parallel because you need the samples. And there are sort of lots of interesting robotics application. I would argue the simulation technology is just fundamentally not there. For example, if you want to do interesting things with fluids or compliant or soft objects, typically the simulators there are either accurate and expensive or like fast and give you completely garbage physics. I think for a lot of the more interesting applications, we haven't quite figured out how to find the balance between solving the problem, just simulating in a fast and reasonably accurate way. And finally, the MPPI, I would argue for MPPI is at least naively, it does not really handle unstable systems well. So for the quadruped systems we showed earlier, that's like basically quasi-statically stable. If you think about a quadruped, essentially like a table sitting there if you don't do anything. Versus if you try the MPPI on a humanoid, it's pretty unlikely to work. At least you need to do a lot of engineering to make. You need to do smart. In that case, you need to do much smarter things with your sampling distribution and that sort of thing to make sure you're sampling on some sort of stable manifold, let's say. So here, this is very naively, if you try and run PPI on a quad rotor directly on the torques, quad rotor is very simple problem, but it is unstable. If you don't do smart things, your quad rotor just falls out of the sky. If you do MPPI on it, the quad rotor can't really find a stabilizing control versus it's the dumbest and simplest thing with LQR. You can take a couple derivatives and gives you nice and smooth controls in closed form. I guess the point I want to make here is that you shouldn't be solving every problem with MPPI. Instead, I would maybe think deeply about the fundamental limitations of the algorithms and sort of what is the task that you're trying to tackle and sort of find the right set of tools for the problem that you're trying to solve. I guess, yeah, sorry.
Does the instability in MPPI for like hardware control come from like model mismatch?
No, it just comes from the dynamics being unstable. Yeah, so basically if you have dynamics have large eigenvalues, essentially. Basically one way to think about this is sort of like MPPI is doing single shooting. So if you have if your A and B matrices, let's say, have like large eigenvalues, and if you do like you multiply A and B matrices like across some time horizon, you essentially eventually get really, really bad ill conditioning, meaning that basically you lose sort of numerical precision, like then you can't really do anything at that point.
Does that work better if you have a shorter time horizon?
It works, yes. So you don't, yes. So if you have in the limit of like, really short horizon, it's fine. But then your terminal cost, you need to have a really good estimate on your terminal costs to make that sort of work well. Yeah, the general, typically, if you want to get around sort of the single shooting ill conditioning issues, one, you can sort of simulate with some feedback policy, which is what iLQR does. Or you can do sort of multiple shooting collocation type thing where you can simulate the unstable dynamics for only a couple time steps or maybe a single time step and solve the general nonlinear optimization problem. There, you don't have to deal with the unstable dynamics. Yeah. So I guess to sort of like, some parting thoughts. These are just me random yapping. I would argue sort of at this point, 2025, the leg locomotion is largely a solved problem. There are fairly standard ways in industry to do these things. The RL toolboxes work extremely well. If you're starting grad school today, maybe pick a little bit harder problem. I think when I started grad school in 2022, it was like, it was getting close to getting things figured out. But I think in the last, I would say year or two feels like every other week there's a cool demo coming from industry. And if you're sort of picking a research problem now, I don't think this is necessarily the best thing to choose. I think I would argue sort of the next frontier is thinking about for these sort of leg robots, human robots, is sort of thinking about how do you do motion planning, control, reinforcement learning, what do you want to do for when you actually have to think about locomotion jointly with manipulation. By that, this is what's so-called the local manipulation. There's some recent work because the human robots have been much more available the last 6 to 8 months. People have been working on trying to starting to think about the local manipulation problem. In particular, I think it's the interesting set of problems are where the objects you're manipulating actually, in terms of size and inertial properties, actually has a large impact on your robot dynamics, such as carrying couches, heavy boxes, and that sort of thing. I think if you're just rocking your humanoid robot in front of a desk and do tabletop manipulation, I would argue that's pretty boring, and that's not you can just have bolt your robot arms to your table and then do the exact same thing in those scenarios. So I think the next sort of research frontier is thinking about how to solve jointly the locomotion and manipulation problems. Where in particular the objects that you're manipulating actually makes a large impact on the overall dynamics of your system. I think in particular, I think the last couple of years there's been a lot of discussion debating between RL versus MPC, in particular around sort of like the idea of RL being sort of model free and MPC being model based. I would argue that's sort of not the right way to think about it. If you're doing sort of RL with some arbitrary simulator that you use, you're sort of inherently still sort of bottlenecked by the simulator that you use. So I think both of these methods are sort of model-based. Instead, I think the right way to think about this is sort of RL being sort of amortized offline computation optimization, whereas MPC, you're doing the optimization online or at test time. I think there are sort of like, it's interesting to think about, what exactly do you want to sort of optimize offline? And my sort of intuition is if you have a good idea of the distribution that you will see at test time, you should sort of probably spend your time, doing a little bit more domain randomization and doing a little bit more work offline, and makes your life much easier at test time. In particular, I think that's like typically the case for locomotion these days. When people train an RL policy, you can train RL policy to walk in like 5-10 minutes, and if you vision-based policy, maybe a couple hours, and sort of that's it. And then you get a very robust zero-shot deployable policy on your actual robots. So I think that's extremely powerful. I think it's interesting to think about, what are the scenarios where, maybe you don't have a good idea of the test time distribution that you see at training time. Maybe that's manipulation. Maybe that's, you can't foresee exactly everything you can possibly manipulate on a humanoid robot when you're training the local manipulation policies. Maybe in some of those scenarios, you could think about doing online model-based motion planning, sort of gives you a little bit more generalizability and that sort of thing. And I think the last point, I think I would argue sort of the robotics algorithms that you use are sort of deeply connected to the robot hardware that you currently have and sort of the compute resources. I think what we showed today, sort of the MPPI and iLQR algorithms are in some sense really, really old algorithms. iLQR dates back to the 60s, and MPPI has been around for at least, let's say, I want to say 10, 20 years, something like that. And the only reason why, we can do the demos that we're doing today is because computers got faster. If I'm traveling with the robot I have today and the computers I have today back to the 60s, and so you can wipe my memory, you can probably still do the same sort of demos back then. So like, when you're sort of, I guess the other sort of the point is that I want to make is that if you're thinking about designing algorithm, it's sort of, good. It's useful to pay attention to the hardware and the compute limits and sort of think about what are the algorithms that can scale with the current trends and innovations in hardware and the computation. And finally, I think the sim to real / real to sim is still a very open problem, and people are still trying to figure out what's the right way to use simulation data versus online interaction data. So I think there's still some very interesting opportunities in that regard. I think that's all I have to say.